All right. Well, I thought it would be neat to look at an application of the Metropolis algorithm, Metropolis-Hastings algorithm, because well, so far we've just been using it to like generate values from like the t distribution or something, right? And it hasn't been. Well, I don't know. Maybe it's exciting. Like maybe that one time I did like the normal distribution, even though like I used a uniform proposal. Maybe that was kind of neat, okay? But I don't know. There might be you might feel like, why are we bothering with this? Like, can't we just really work out inverse CDF or something? Well, so I'm going to give us an example where I don't think there's, if we're not going to use the Metropolis algorithm or some kind of MCMC method, I honestly don't know how we would approach this problem, okay? So I'm going to just look at, we're going to look at an application of the Metropolis algorithm, okay? And it comes from this, this paper by Percy Diaconis, okay? All right. And so this is what we see, all right? And what this is what I think this, oh, okay, yeah, so this was a message that was intercepted by the state prison system, right? So it's like high stakes message passage, right? So like in high school, I don't know, you guys were good kids. You probably didn't pass notes to each other. Maybe you did, okay? But then like if you passed notes to each other, your teacher could intercept it and read it and embarrass you or something. Like, and if you're in prison and you're trying to pass a note to somebody else, like you definitely don't want the guard to intercept it. But anyway, so what they did was they said, okay, well, we're gonna write in code, okay? But so this is what they wrote, okay? They wrote stuff like this. This looks like a Pigpen cipher, but anyway. So they wrote stuff in this code so that when it got intercepted, the guards would be like, I don't know what this is, right? So anyway, the employees at the state prison, they brought it. And then the statistics department at Stanford said, "Oh, maybe we can help you out." Okay. So what was I saying? Oh, so I don't know if you guys ever did ciphers as a kid. Like I feel like probably in 5th grade. If you were like into like spy stuff, you might have done this. Like you would have said like, you know, you would come up with a cipher and you're going to say like A is going to be this, and B is going to be this, and C is going to be this, and D will be like this, and I don't know. You would come up with some kind of thing, and you'd get like this decoder ring, and then you would like each letter you would have to look up what symbol you're going to write. And then you pass it to your friend, and your friend gets the thing, and then they have to decipher this, right? This was like a Christmas story. It was like, drink more Ovaltine or something. That was the disappointing secret message. And so basically, the idea is each letter has been replaced by a symbol, okay? So this is not encryption. Don't think that suddenly we're going to learn how to crack encrypted messages. This is not encryption. This is just replacing one letter with another character. Okay, so it's not sophisticated. Okay, you might have even done. So this is kind of one kind of possible cipher. You might have even said like A. There's like A can become the letter N, and B becomes like the letter K, and C becomes the letter E or whatever, okay? And you could have just replaced one letter with other things. You do this for all 26 letters, okay? And so here's the question. Can we use MCMC to try to decipher this, okay? We want to decipher. Decipher a message. Okay? So, again, when we talk about cipher, we just mean each letter has been swapped for it with another letter. Okay. And probably after you sent like one message, you realize like, oh man, this is a lot of work to like cipher and decipher, and that ended your days as a pretend spy. Okay, so this is what we want to do, okay? So the thing that we want, okay, we want to find the correct cipher key. Okay, we'll call this this. And this is going to be, we want to find the correct mapping of one letter to another letter. Okay, so we want to find the correct cipher key, which, and this is how we have mapped letters to other letters, right? Okay. And so, you know, if you have it like this, then to cipher, you have to go this way, and then to decipher, you have to go the other way. Okay, so you go, A becomes N, and then to decipher, you have to say, well, N goes back to A. All right, so how are we going to find the correct cipher mapping? Okay, so what we will do, so basically we've got a Bayes problem, okay? Bayes formula problem, okay? I don't know if this is Bayesian, but so what we're going to say is that we want to find the most probable mapping given kind of the ciphered text. Maybe I'll call this the scrambled text. Okay, so, and we want to find like what mapping, we want to find a probable mapping All right, and so what this will be, using Bayes' rule, we're going to say this is going to be the probability of the scrambled text given some mapping multiplied by a mapping, probability of a mapping, divided by the probability of getting scrambled text. Okay. All right. So this is, believe it or not, this is what's going to solve our problem. Okay. Okay, well, let's just think about these mappings. Or let's think of our space, our domain, our probability distribution space. How many mappings are there, right? So if we're going to just say we're going to take the letters A, B, C, D, E, F, G, all the way up to X, Y, Z, and what we're going to do is we're going to map them to just different letters. Okay? How many mappings are there? 26 factorial, right? 26 factorial possible mappings. Right? Because there's basically 26 possibilities here. Once I have 26, then there's 25, 24, etc., 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 down to 3, 2, 1. Okay, so 26 factorial is a really big number. What is it? Let's ask Google. 26. Okay, it's on the order of 4 times 10 to the 26. Okay. 10 to the 26. Does that number even have a name? How much is it? A billion is 10 to the 9. Trillion is 10 to the 12. My brain can't even do anymore. A trillion trillions? I can't comprehend this. Okay. That'd be 10 to the 24, I guess. Okay. All right, so there's 26 factorial possible mappings, and that's just like way too many to try, okay? Yeah, I know, there's like people who are experts at deciphering stuff, okay? But basically, the number of possible mappings is too big to, quote, brute force. All right, and so what we want to do is we want to find a way to evaluate certain mappings, okay? We're going to, we want to find a way to kind of evaluate the likelihood of a mapping. So we get the likelihood times prior divided by the marginal. All right, so how are we going to measure the likelihood, okay, of our scrambled text given a certain mapping? Okay, so how do we evaluate this thing, right? What is the likelihood of getting some text given some mapping, giving a mapping? Okay. All right, so this is how we're going to approach this. Right? There's a few ways to think, right? So if the mapping will take our scrambled text and produce real words, we want to say this is a good mapping. Okay? So I mean, obviously, right? So if the kind of, we're going to say just some, if the proposed mapping is able to create some real words out of the scrambled text, okay, we want to say this is good. Right, so let's say your text is K, S, V, and G, right? And then let's say the mapping, okay, we have two possible mappings. So one mapping, we'll say this turns into H-O-U-S-E, right? So we're going to say H goes to K and et cetera, et cetera, et cetera, okay? And then another mapping says when you decipher, it turns out to be H, N, S, X, Y, okay? We're gonna say this one's bad, right? So this is good, bad, okay? This is good because we got a real word, okay? So if we see real words, a good sign, okay? And one tool that we're gonna use is we have a word lexicon, kind of listing. I don't know how accurate this thing is, but it's more accurate than having nothing. It lists off kind of like high probability words. So words like the will have a high probability, okay? And words like house will have a medium probability. And other real words, I don't know, that might be rare, a little bit more unusual, like something will be in the thing. They'll have a non-zero probability, but you know, we'll have something lower. Yeah.
Where's this lexicon like data from? Like just in general, because let's say you look at like children's books, might be different probabilities.
Yeah.
Words you might find in a prison.
Yeah, absolutely. I actually don't know where this was generated from. Okay, looking at it, I suspect somebody created it by scraping Wikipedia, because there's like certain words that are a little bit more common on Wikipedia. Or like in Wikipedia, you have like these references which are like single letters, and like the single letters all have fairly high probabilities, which I'm not 100% sure where this came from, but we're just gonna hope it's like halfway representative, okay? At least as far as like super common words like is and the and stuff like that, okay? These things will be will show up, right? So if we see real words, this is good, okay? And we're gonna have use a word probability lexicon. All right, there's a significant flaw though. It doesn't have plurals, and it's like a huge issue. But our thing will still work. So even though our lexicon is a little bit crappy, it's still like it's enough to get us to do our job. Okay, so like if I look up lexical database, it's a huge list, and I can look up like lexical database, the word the. Okay, and so this shows up. It says the has a kind of a relative probability of around 5%. Okay, I guess one, you know, and then if I do something like house, then that's 0.0004. Or if I look up other words like houseboat, okay, it's not 0. Okay, much lower probability, right? So people are much more likely to use the word house than they are to use houseboat. What are these other words? House, wait, okay. Houseboat, houseboating, housebound, houseboy, what? I don't know what that is. Okay, housebroken, house builder, house Carl, house father, housefly, household. Okay, so household, you know, is about 1. Okay, so I don't know where this thing came from, but it's it's still useful to us, right? All right, what do you think? House versus mouse. House is 0.0004. Which one is more probable, house or mouse? House, right? Let's see. Oh, yeah, by far. Okay, all right. So anyway, what other words would be, okay, well, it doesn't matter. All right, so we have this. So we're going to, word probability lexicon, and this gives us basically probable words will have high probabilities, like the, okay, will have high values. Okay. All right, and so this is going to help us decipher, and basically, you know, if you were deciphering something, you would try to look, like the strategy is to look for these 3-letter things and say, like, these are probably the words the, or something like that, okay? Or like if you see letters all by itself, or characters all by itself, you're gonna say, okay, this is probably I or A, or something like that, right? And that's kind of a strategy. We won't even bother with that right now, okay? We're gonna just say, let's see if we can do this. So that's one way to go, okay? One thing that we have to do is that even if we get some bad translation like this, we don't want to say, well, this word does not exist in my lexicon, so this gets a 0 probability, okay? We want to give it a small probability, but not 0, because as soon as you multiply by 0, it zeroes the whole thing out, and you're in trouble, okay? So we want to give it a small number, but not 0, okay? So we also give small probabilities, small but non-zero, and it's important that it's non-zero. Probabilities to nonsense, like HNSXY, okay? Because I probably should have picked different letters. Probabilities to nonsense like this, so we do not get 0, okay? Because as soon as you multiply it by 0. So we're gonna, you know, look for words, take their probabilities and multiply them as part of our likelihood. Okay, so far our kind of the probability of the scrambled text given the what did I call it? The cipher key or the mapping, cipher mapping. This can be kind of the product of kind of probability of basically words that appear. Given the cipher mapping. Okay, so the scrambled text, we're going to take that and do that. Okay. There's an issue though, is that in the beginning, you might have one cipher mapping and you might have another cipher mapping, and both of them just produce like total garbage, okay? Like you get no intelligible words out of this cipher mapping and you get no intelligible words out of the other cipher mapping, okay? Does that mean both cipher mappings are equally bad? Probably not, okay? Probably one of them is less bad than the others, right? Okay. So the other part is in the beginning, you know, proposed cipher mappings may all produce garbage. Okay? But some garbage is less bad than others, all right? That's kind of our key idea here. Okay, so I don't know if you remember when I tried to do the Metropolis algorithm to generate values from the normal distribution, I think I started off at like -20, or somewhere far out, right? So if we say, you know, could a standard normal distribution produce negative 20, we go, no, that's a garbage value. Could it produce negative 19? No, that's also a garbage value. They're both garbage, but negative 19 is less bad than negative 20, right? And because we have that ability to say negative 19 is less bad than negative 20, we're going to pick negative 19 over negative 20. And then when we're at negative 20, it's still a terrible value, and we might propose negative 18, and we're going to say, well, negative 18 is less bad. And so we're going to be moving in the right direction until we finally get to around like negative 3 and negative 2, and we're like, okay, negative 2, that's a reasonable number for the normal distribution to produce. And so here, we're going to, in the beginning, you have a certain cipher mapping, it's going to produce garbage text, all right? And you have another cipher mapping, it's going to produce garbage text, okay? But, so let's say, you know, we've got, I don't know, V, B, G, I, R, okay? And, okay, so one map versus another map. Okay, and this one maybe will produce T, O, U, K, L, okay? And this other one will produce J, G, F, X, P, right? And neither of these are real words, okay? Neither of these have produced real words as far as these 5 letters go, but I think we would all be in agreement that this looks more like English than this, right? So, so both maps failed to produce a real word. But TOUKL looks better than JGFXP. All right. So, so why does TOUKL look better than JGFXP? Well, it has vowels, okay. But there's a certain thing is that in English, we expect like certain letters to kind of go together, like T and O, like that makes sense, right? And seeing J followed by G is a weird thing to see, okay? I don't know, are there any words where you spell it with a J and then a G? I can't think of any, all right? But maybe you can, all right. So, in English, certain 2-letter combinations are more likely to appear than others. Okay, even if I didn't have vowels, like if I had TH, R, what else could follow? R, I don't know. PS, okay, versus, even if I use the same letters, okay, if I have S, R, H, PT, okay, like I think we would say this ordering of letters seems better than this ordering of letters, right? Because R followed, like T followed by H seems a lot more likely than any of these other kind of letter combos as well, right? So I'll just get rid of these because I think that would be confusing to have in the notes. So anyway, certain 2-letter combinations are more likely to appear than others. And so what we're going to do is we're going to try to figure out which two-letter combinations are more likely than others. And we'll also use that to inform us, right? So our scrambled text will be kind of the product of the words that appear, plus we're going to also look at kind of the product of the probabilities of basically our two-letter combos given a cipher mapping. I mean, there's all sorts of things you could have done, but I'm just going to start with this. So we're going to say we're going to look at two-letter combinations, and if we see two-letter combinations like TH, we're going to say that's good. Letters like IN, that's good, okay? But if we see JG, we're going to say that's bad. PQ, bad, all right? Okay, QU, we'll say, all right, that's good. But other letter combinations will vote down, and certain ones will vote up, okay? That's actually this concept of having letter combinations is what made the iPhone possible. Back in 2007 when it was first released, they were like one of the first phones where you had an on-screen keyboard, okay? And everybody uses an on-screen keyboard today, and you don't realize the statistical magic that had to go into it, all right? So, I don't know how old you guys would have been. In 2006, even 2007, when the iPhone first came out, the BlackBerry was very popular. I don't know if you guys remember seeing a BlackBerry. And so a BlackBerry had a physical keyboard, and you could use your thumbs and you would push those, right? And you'd push the buttons and it would type out the message. And people liked physical keyboards because they thought they were a lot more accurate than on-screen keyboards. And at that time, it was true. But then Apple, they had a brilliant innovation that dramatically improved the accuracy you would get on a physical keyboard. You could try this on your phone, okay? Pretend like you're going to type the word the, T-H-E, except after you type the T, tap the space in between the G and the H. Rather than the H key, tap the space between the G and the H. And then the phone will enter an H. Or did it enter a G for you? It entered a G, but I'm trying. If you tap, you can try on your phone, tap the T and then the space in between the G and the H, and more often than not, it will enter a TH rather than the G, okay? And what's going on is that even though the screen looks the same, after you tap the T, internally, the touch sensitivity, like the area of the keyboard that gets mapped to the letter H, grows, and it's bigger, okay? And then, and it changes for every single letter that you type in. After you type in each letter, the mapping of where your finger touches, what letters they map to, adjust, okay? And it's based on kind of studying the English language and that, okay? So, you know, if you type in so you can try typing like between the T and then the G and then between the E and the R, and it will probably get in the word the, okay? Because it's expecting something like that. All right, okay, so this is what we're gonna do, all right? As far as this part goes, the likelihood, okay? So I have probability of a mapping given basically the ciphertext. And we're gonna say this is equal to the ciphertext given a mapping. So what's the probability of getting this particular ciphertext if we have a mapping times the probability of the prior probability of a mapping divided by the ciphertext. Okay, this mapping part, the prior, P of a mapping, is the idea of, is a particular letter mapping more probable than other particular letter mappings? Before you even look at the data, Like, is there any reason to believe that we're more likely to map certain letters to certain letters? And I would say probably not, okay? So prior to looking at the scrambled text, I don't think we have any reason to believe that the letter A should be mapped to the letter K, then it should be mapped to the letter J or the letter P or some other letter, okay? So as far as the priors go, I would say we have, no reason prior to looking at the data, no reason to believe one mapping is more likely than another. Okay, so as far as the prior mapping goes, I'm going to just use a constant. I'm going to just use basically constant. And technically the constant is going to be 1 over 26 factorial, but I'm just going to ignore it, okay? Because as far as this goes, the ciphertext times the probability of mappings, the denominator also, okay, the marginal, again, is some constant, and it's going to be the sum of the numerators, right? Which is going to be the sum of basically the likelihood times our p mapping constant, which is a constant, okay? And so this is a constant, so basically it just boils down to that the posterior probability of a mapping given a ciphertext is just proportional to the ciphertext, the probability of producing the ciphertext given a particular mapping. Okay, and the way we are assessing the probability of the ciphertext is we're going to say, are we getting original, like real words, and are we seeing letter combinations that appear likely? Is this part okay? So, so as far as the letter combinations, okay, I'm going to have basically a 27 by 27 matrix. It's going to be the letters A through Z plus a space. A through Z and space. And we're going to say, okay, what's the probability that, in this spot is, what is the probability of basically A follows the letter A? Okay. And then AB will be probability that B follows an A. And then AC, probability that C follows an A. Okay, all the way up to, and this is basically probability that word ends with the letter A. Right. So it's going to be very different for different languages, right? So in English, some words end with A, okay? But if we were talking about Spanish, like a lot of words end with the letter A. So, so this is what we have, right? In English, probably a lot of words end with the letter N. I don't know. I think that's like the most common thing. All right, and so to do this, we're gonna build this up by scanning a huge chunk of text. So I think I got like the English translation of War and Peace. Okay, so which is this very long book. Originally in Russian, but then we translated it into English, and we're hoping that this will at least give us something sort of representative of at least the two-letter transition probabilities that we'll see in the English language, okay? So we will go through each line and look at two letters, and basically, and every two-letter sequence, we're going to just put in tallies in our big matrix. Okay, so, you know, if I look at this word, we're going to go en, we'll put a tally at en plus 1, okay? And then we'll go to ng, and then we'll add 1 to that tally, and then we'll go look at gl, and then we, you know, plus 1, and then li gets a plus 1. And we go through, and we go through the entire text, 2 letters at a time, adding a tally to each thing. I think we tell it to like ignore all punctuation and stuff like that. All right, so this is how we're going to get our letter combinations. And as far as the lexicon goes, we're going to assume that somebody has created it for us, and I don't know how accurate or trustworthy it is, but it seems at least workable and reasonable to have. So I guess I'll just we'll look at the, I'll load up War and Peace, and so we won't get to finish, but as far as War and Peace goes, we're going to turn everything to uppercase. I'm going to build up my empty two-letter transition matrix, okay, and this is I don't know how to do this. Okay, and this is kind of the code that we're going to go, okay? So every 1,000 letters, we're going to print something to the screen just so that we know that, or every 1,000 lines, we'll print something to the screen. And we're going to go for position and 1 through number of characters, okay? So, you know, we look at a particular line, so we're going to, for each line, we're going to look at each position. So we're going to go do this loop, each line, 1 line at a time, in each position, and then we're going to basically subset the, our current letter will just be, you know, the first letter, and then we're going to go to, we kind of get our next letter, and basically, if we find it there, we're going to add 1 to that spot, okay? And if not, okay, then if it's not a letter, then we're going to go to add something at the space, okay? So if it's like if we see the letter A and B, you'll add a 1 to AB, okay? And if the thing that comes next is not a letter, and you know, then we'll add something to kind of the space. So anyway, we can kind of do this and build this up, and it will it'll take a little bit of time, but I just kind of want to show you the thing that that results. Oh, okay, and then the last thing we're going to do is we're going to add 1 to every single cell. So there might be some letter transitions, like, I don't know, QV, that never appears anywhere in our thing, okay? But again, it's very dangerous to have 0 probabilities, so we're going to just add a 1 to every single cell in the thing, and, okay. All right, maybe we won't finish, because I think there's like 60-something thousand lines of text. Although we're like halfway there. And we can plot it, but basically what we'll see is like the TH transition will be high, other things will be lower, stuff like that. Here, can I just stop this? Will this still work? Let me just see if this produces a plot here. Okay. All right, so we see the letter T followed by H is very probable. The letter H followed by E, very probable because of the words the, right? I followed by N, E followed by R, okay? Letters that involve J, very low probability, okay? E is followed by a lot of other letters and stuff. I guess E is not often followed by J or K, and it's not often followed by O, but and stuff like that. Okay, so you got basically this mapping, and we're going to use this for our two-letter probabilities. Okay, we'll continue this next week, so have a good weekend, and we'll see you then.